An understanding of the load and store operations is vital to being able to take advantage of the Neon instruction set. Notice that the load and store have this common LT and ST, just like we had with the ARM processor, but there's a little bit more to the instruction than just the LD or the ST. Notice, of course, there's the V that's in front of both of these guys. That indicates that it's a vector operation. But this little lowercase n that's at the end of each one of these guys, well, this right there identifies the interleaving. And if you remember from our earlier discussion, our interleaving allows us to grab every element or every other element or every third element or every fourth element. So n is equal to 1, 2, 3, or 4. Now, if you recall, just a straight vector, the elements of the vector are just stored in consecutive positions in memory. That would be a 1. If you have something like left and right channel stereo data, that would be 2, where the left channel would be alternating every other one with the right channel. RGB data would be good for the 3, and our red, green, blue, and alpha data would be good for the 4. But we identify the interleaving for which we are going to load or store these values with this little lowercase n, which is really included as part of the instruction. As I said before, the ARM conditional expressions, the not equal or the equal or the less than or greater than and so forth, that is going to be, you're still allowed to put those at the end of the instruction, right immediately after the interleaving. Then we have a period, and these periods identify or separate the instruction. And my big fingers sort of hit everything here. Let's move back down to this appropriate screen. There we go. The data type, you think of data type as integer or floating point or double or signed integer versus unsigned. This is really just the size of the data. In other words, I am going to be loading 8 bits, and this is important with the interleaving, of course. So I'm going to be loading 8-bit values, I'm going to be loading 16-bit values, or 32-bit values, or 64. Actually, it might not be 64. The next page will tell us. But anyway, the data type just simply gives me the size of the memory, just the size of the element. So if I have a vector of bytes, then there's going to be an 8 there. If I have 32-bit integers, then that's going to be a 32. If I have 32-bit floating point values, that's going to be a 32. But I don't need to identify whether that's a float or an int for the load operations. For the other operations like add and so forth, yes, but for loading, we just simply put the integer value. And then the list here, this is going to be identifying the vector registers. So you're going to get a list, and the list may include more than one register, but it's going to be a list of all the registers that you're going to load with the values you're pulling from memory or store from with the values you're writing to memory. Rn, this is the pointer to pointer to the location in memory that we're interacting with. So the starting location. These optional values, I can have an optional exclamation point. The exclamation point says, after I'm finished loading the list of vector registers with the values that are located at the memory location pointed to by Rn of size data type with the correct interleaving, then if there's no exclamation point there, nothing changes. But the exclamation point says to update see if I can erase this. There we go. To update Rn. So after we have done the operation, do I want to put in Rn that pointer register? Do I want to put the location of the next section to load? I did the demonstration earlier about where I had a full register, and so if we want to load our 8 values, so we load 1, 2, 3, 4, 5, 6, 7, 8. So let's say I load those values. Rn was originally pointing to this first location here. If there's no exclamation point at the end of this operation, it's still going to be pointing to that register. With an exclamation point, however, it is going to update Rn so that it is now pointing to the next block to load. Rm is slightly different. What it does in this case is if we've got a value in Rm that we want to add to the Rn after the load operation, then by putting the register there, what we're going to do is actually take the value that's in Rm and add it to Rn. So let's look at a couple of examples. So here's an example. We're going to do a vector load with an interleaving of 2. So that means that if I'm looking at memory, then what I'm going to do is I'm going to load every other value, right? The data type of 16 says that the number of bits is 16, and then I'm going to skip 16, and then I'm going to load 16, and then skip 16. Now, of course, this is in terms of bits. So actually what it is each one of these guys is going to be 2 memory locations for 2 bytes. Then D0, D1, this is the list of registers that we're going to populate with these values we're loading from memory. R0 contains the address that's pointing to the very beginning of this list. There is no exclamation point, so after this instruction is completed, R0 is not going to be modified. So let's see what this looks like in terms of some examples. Let's assume that I do have data stored in memory sequentially that is red, green, blue. So red, green, blue, element 0, red, green, blue, element 1, red, green, blue, element 2, and so forth. So this is the color of 1 pixel, basically the first pixel. This is the color of the second pixel. This is the color of the third pixel, including this piece down here, and so forth. So if I just go ahead and do a vector load with an interleaving of 1, size of 8, there are the 3 registers, the vector registers I want to load, and R0 points to the beginning address where these guys are located, then R0 is pointing to the location in memory where red for pixel 0 is located. Since there's an interleaving of 1, that means there's going to be no skipping. There's going to be no every other or every third or every fourth. We're loading these one at a time directly from memory. So a byte goes into D0 from R0. A byte goes into D0. A byte goes into D0, and all these bytes are all in order. We're going to continue to do this operation until all D0, D1, and D2, till all 3 of these guys are filled with the neighboring bytes from this vector that is pointed to by R0. Well, as I said before, it might be kind of nice to be able to, using the load operation, separate the red from the green from the blue. The only thing we need to change in this operation is our interleaving. Everything else should be exactly the same. So I go to the next slide, and the next slide shows that I now have an interleaving of 3. Everything else is exactly the same. Still the same byte size, or data size, still the same register list. We're still loading D0, D1, and D2. Still the same pointer. This time, however, we're going to load R0, jump over G0, B0, and G0 and B0, and load R1. But actually what we're doing is we're loading 1, 2, 3 like that, then up to 1, 2, 3, and then up to 1, 2, 3, and so forth. So the interleaving, by having 3 registers here, makes it so that we actually, with a single instruction, separate that data into 3 separate vector registers.